All right, so on this video, going to look at graphing parabolas and actually going to approach it from two different perspectives because both of these are common, both of them are useful, and let's see how they relate to one another and how these two slightly different tools can be used. So a parabola is any graph of a function of the form y equals ax squared plus bx plus c. And it turns out that those are all functions, and all of them can be shown to be parabolas. The way we know that they're parabolas is, well, first of all, y equals x squared is your basic parabola, which see here. Of course, I could have done a much better drawing, but you've seen it before, I'm sure. If x is 0, y is 0. If x is 1, y is 1. If x is negative 1, y squared negative 1, you get 1 also. So it has symmetry about the y-axis, and it's called the axis of symmetry. And if you were to fold y equals x squared on a piece of graphing paper, graph it, fold it on the y-axis, the right side and left side would coincide. If you compare that to the graph of y equals the square of the quantity x minus 4, that plus 5, as you should know, the minus 4 here shifts the whole graph 4 units to the right. And the plus 5 outside of the squaring shifts the whole graph. By the whole graph, I mean this graph here. Shifts it up 5 units. Shifted 4 units right, 5 units up. And therefore its vertex, well, the vertex is the turning point here. That's literally what the Latin term vertex means, the place where the graph changes direction or turns. And that occurs at 4, 5. So it has the same overall shape, but the vertex has been moved. And of course, every other point on the graph would likewise move someplace. The graph has a point at 1, 1. That would move to 5, 6 in this case here. You plug in 1 minus 4 is negative 3. Square that, you get, is that right? 1, 1 should shift to 4, 6. No, should. Well, anyway, the point at 1, 1 would shift 4 units to the right and 5 units up. So that would take it to 5 and 6. If we multiply that by negative 10, not the whole thing, but just the squared part of it, that's going to have the effect of, well, the negative's going to turn things upside down, reflects it off the x-axis, but the vertex would stay at 4, 5. So something like this. Again, really poor drawing, but just to sort of capture the rough idea. The drawings don't have to be perfect. That's what graphing paper's for. The important thing is the vertex stays where it's at. It doesn't move. Okay, so how do you find the x and y intercepts of something like this? So if you look at my graph, it's poor again, but it does cross the x-axis. I know it has to because from the negative 10, I know that it's going to be concave down, it's going to open down. The vertex is up here at 5. Well, if the parabola is opening down from 5, then it has to cross the x-axis. Not all parabolas cross the x-axis. If you're looking at this one, for example, the vertex is at 4, 5. Well, the x-axis is down here. You can see from the orientation of the parabola, it will not cross the x-axis. But this one does. So the negative tells us that. Also, the 10 has the effect of what we call a vertical stretch. So if you're comparing it to this one, it's going to be taller, so to speak. That's just a matter of speaking because, well, is it really taller if it's infinitely tall? But it would definitely look narrower if you're plotting, say, negative square of x minus 4 plus 5 on the same coordinate system as negative 10 times the square of x minus 4, that plus 5. This one is narrow, the other one would be wider or shorter, depending on your point of view. Well, it wouldn't be shorter because it's going to still go up to 5, but go ahead and graph both of them. Take a look at them. You'll understand what I'm talking about if it's not clear. Okay, well, how do you find the y-intercept? Well, you plug in 0 to find the y-intercept because the y-intercept is on the y-axis. Every point on the y-axis has the next coordinate of 0. X equals 0 is actually the equation of the y-axis. Well, if x is 0, we just do the calculations here. Plug in 0, 0 minus 4, of course, is negative 4. Square that, you get positive 16. Multiply that by negative 10, and you get negative 160 plus 5 is negative 155. Should check my arithmetic on that, but it's actually not that hard to do mentally. So f of 0 is negative 155. In other words, the y-intercept is 0, comma, negative 155. So if you look at my graph here, well, if we were to follow this part down, it would eventually, so if this is 5, then negative 155 is quite a ways down there. And we'll look at the graph later, but in a more detailed, more professional, more accurate graph. So how do you find the x-intercepts? So over here, I just labeled them as x1, 0, x2, 0. I know there are 2 of them from looking at the picture here. The x-intercepts, you either have 2 x-intercepts or you have no x-intercepts, which would be the case if this were a concave up parabola passing through 4, 5, like I mentioned this one. Or you can have exactly 1 x-intercept. And if you think about it, and you should think about it, what's the point in studying math if you're not going to take the opportunity to really think as deeply as you can manage about the things you're dealing with? Well, if we have, I think I can move this. I don't need more room here. The way this writing program has, or drawing program has done things. If I move my axes up here, if the vertex were to hit the x-axis, then that would be simultaneously the vertex and the 1 x-intercept. So it can happen where you have exactly 1 x-intercept, but the only way that can happen is if that is the vertex. And of course, you can also have a situation like this where there is no x-intercept. 2, 1, or none. Anyway, as already mentioned, in the case of negative 10 times the square of x minus 4 plus that plus 5, we get 2 x-intercepts. So where are they? Well, the go-to trick for finding the x-intercepts of a parabola is to use the quadratic formula because the x-intercepts correspond to y equals 0. Just as the y-intercepts correspond to x equals 0, the x-intercepts correspond to y equals 0. Which is one of the reasons that I went ahead and labeled these 2 points here, even though we don't know what x of 1 is or what x of 2 is. We set y to 0. Well, just generally you set y to 0. The quadratic formula will always answer the question, what makes y equal 0 in a quadratic? But there's an easier way of doing it here than the quadratic formula, because if we just go through the process of solving the equation and make use of the square root property at the appropriate time. If we have negative 10 times the square of x minus 4 plus that plus 5 equals 0, well, subtract 5 from both sides of the equation, and we have this one here, negative 10 times the square of x minus 4 equals negative 5. That equation we can solve by dividing both sides of the equation by negative 10, first of all, which gives me x minus 4 quantity squared equals 1/2. And then apply the square root property. I mentioned the square root property in my last video where I looked at completing the square. If you take the square root, by the square root property, we actually get two different solutions, plus or minus. So always remember when you're taking the square root to solve a quadratic equation, you want to look at both square roots. In this case, they're the square roots of 1/2, which turns out to be about 0.707. I just put it in here as a 0.71, so we have plus or minus that. Well, to finish solving this, we just add 4 to both sides of the equation. The exact solutions, they can be written up in a variety of different ways depending upon what you want to do with that radical. You may be familiar with the idea of simplifying a radical. So that the square root of 1/2 is written as radical 2 that over 2. However, I don't see any need for it here, so I'm just going to leave it in the unsimplified square root of 1/2 format. Then we have 4 plus or minus that number. So these numbers, again, are about 0.71 and negative 0.71. So if you add 0.71 to 4, you get, of course, 4.71. And if you subtract 0.71, both the negative radical, you get approximately 3.3, 3.29 is the way I wrote it down here. Okay, so then what do we have? Well, I also want to look at this from a slightly different perspective. So everything here was written in what sometimes referred to as vertex form. I think I've seen it in textbooks called something different. It's pretty common to think of this just generically. Let me grab this real quick here and copy and paste and make a slight change here. Well, it's more than a slight change, it's more of a symbolic change, let's see. So in a textbook, you're likely to see it written up like this: y equals a times the square of x minus h plus k. H and k are really common for shifts in a situation like this. So the vertex is at hk. In retrospect, let me go ahead and grab that word vertex here and copy that also, and go ahead and put that in here. So hopefully you've seen this before. If it's written out in this vertex form, y equals a times the square of x minus h, that plus k, then the vertex is at hk. What you want to note here is that we have minus h, but plus k. And that has to do with the fact that most of our transformations, if they're written in a format where you have a function where you have y on one side and everything else on the other side, well, the y shifts are going to be in the direction you might think. So that plus k is k units to the right. That's not entirely true because we don't know whether k is positive or negative, but I'm going to pretend. Let's assume that h and k are both positive, as in the case of 4, 5. Well, if that's what we're dealing with, then the plus k will be k units to the right. That's going to be k units up, I should say. Whereas the minus h is going to be h units to the right, which means that the k is moving in the direction you'd expect, plus being up as far as y is concerned, whereas the h is going in the direction you wouldn't expect. the minus, you might think, well, that's going to be to the left. Nope, it's going to be to the right, actually. It's contrary to what you might expect. And similar sorts of things happen. So the 10 here, if you think of applying it to y, it stretches things. If you think of applying it to x, which you can do, then it would actually compress it. So it's worth thinking about a little bit, making note of it. Often we just memorize this, but always remember to double check your work here and see if it's doing what you think it's going to do, because the x transformations tend to work backwards of what intuition or common sense might tell you. Okay, so anyway, this is one way that a parabola can be written: y equals a times the square of x minus h plus k, and it has the advantage of having the vertex right here. The a, the h, and the k are sometimes referred to as parameters in this situation. P-A-R-A-M-E-T-E-R, parameter. Same para that you see in parabola. It's the same combining form, P-A-R-A. Means alongside or beside, usually in the translation of the Greek para. What's a parachute? You can look that up. Let me know. Okay. Anyway, the parabola has these three parameters because it turns out we need 2 points. So, for example, if you're looking at a linear equation, y equals mx plus b, there are two parameters, m and b. That goes along with the fact that 2 points determine a line. A parabola, it turns out you actually need 3 points to determine it absolutely. So a, h, and k are the three parameters. They kind of correlate with the fact that those would need those 3 points to determine the parabola. What I mean by that is if you have 3 points that are not on the same line, there's exactly one parabola that can be drawn through those 3 points. Okay, so we saw how to find the x-intercepts in the vertex form. You really just solve the equation. But I want to point out that frequently the parabola is written out in a different format entirely. If we go ahead and square out the x minus 4, then multiply it by -10. So that's what I've done here. So if you square x minus 4, you get x squared minus 8x plus 16. It's x minus 4 times x minus 4. If that's not clear to you, you definitely want to sit down with paper and pencil and multiply this out and see that that's what you get. If you then multiply that by -10, we have -10x squared, -10 times -8, 80, -10 times 16, -160. Add 5. You can see here we get -155. You may remember that from before because, well, now we can see if x is 0, this term 0, this term 0, y is -155. If you have this, so this is typically referred to as ax squared plus bx plus c form, or sometimes called standard form. And that, of course, is the familiar format for the quadratic formula. Something a times x squared, something else b times x, and then a third number c, which doesn't involve x at all. Which, of course, a, b, and c makes more sense than what we have up here with the, where was it? Way up there. Did I pass it? There it is. A, H, K. Why are we mixing A with H and K? It seems to have nothing to do with the alphabet whatsoever, and really doesn't have anything to do with the alphabet whatsoever. But won't worry about that. Anyway, back to scrolling back down here to this. Y equals ax squared plus bx plus c. The c will always be the y-intercept if you have it written out in that particular format, because if you plug in x equals 0, c is all that's left. Now, on the other hand, if we set y to 0, as I already mentioned, you can use the quadratic formula then to solve that. we'll get the same result as we did before. So just to remind you of the quadratic formula. There's actually a couple of ways you can write this out. The familiar one, which is easiest for computations, plugging into a calculator especially, is this minus b plus or minus the square root of the quantity b squared minus 4ac, all divided by 2a. You should have that in your memory, your physical brain memory, if you don't already have it. So if you hadn't memorized this before, or if you'd forgotten it, you should seek out some exercises to practice until it gets to where it's just something that you have memorized. You can also break it down to two fractions, which I have here, which actually helps us to understand the symmetry. It turns out that the axis of symmetry is given by the equation x equals the opposite of b divided by 2a. So for any parabola, that's true. The axis of symmetry is minus b over 2a. The vertex is on the axis of symmetry. And we can actually see the symmetry here in terms of, well, this would give us the x-intercepts. And I don't think I actually did the calculations here anywhere, no. But if you were to plug in the negative 10 for A, the 80 for B, and the negative 155 for C, which you should do, you'll get the same results we got before of about, what was it again, negative, no, they're both positive, 4.7 and 3.3 roughly. The b squared minus 4ac is referred to as the discriminant because it discriminates between different sorts of situations. If the discriminant is 0, that tells us that there's only one x-intercept, which of course would turn out to be the same thing as the vertex. If b squared minus 4ac is a perfect square, then we get two solutions to this equation which are rational. On the other hand, if b squared minus 4ac is positive but not a perfect square, then we get two solutions which are irrational, and they show up as pairs like actually what we have here. Our solutions are irrational, and there's a pair of them. 4 plus the square root of 1/2, which is an irrational number, and 4 minus the square root of 1/2. And again, the square root of 1/2 is an irrational number, so if you subtract it from 4, you get another irrational number. So although I approximated these with the rational numbers 4.71 and 3.29, so both of those are rational. And I really should have used it as approximately equal to symbols like I did up here, but I just wrote them down as equal, which is not strictly true. If you carried them out to however many decimal places you wanted to and just wrote the answer down, it's not going to be correct. It'll only be approximate. But don't want to go into that right now. It's a long story. Okay, so anyway, the vertex is right here, the minus b over 2a. The x-intercepts, if they exist, are to either side of that. Now, if the discriminant is negative, then we're going to actually have imaginary the square root will be imaginary numbers. In that particular situation, we don't actually have x-intercepts. So for graphing purposes, we would then ignore the results of this. Or if you're just solving the quadratic equation, a quadratic equation using the quadratic formula, if you get imaginary solutions, then depending upon the situation, if it's a practical situation, it probably tells you that there's something wrong with your problem setup, that there's no real solution to it. But when we go into more detail about polynomial functions in general, it turns out that quadratics in a certain sense will always have two zeros for the function, or two solutions to the quadratic equation, but you have to count them in kind of a weird way, which has to do with multiplicity, and get into that in a future video, which should be coming out soon here. Anyway, I'll just finish up this video by taking a quick look at, I'm going to change the screen share to a new share, and I'll look at GeoGebra. And I actually put in our function here. I typed it in down here in the input bar originally the way I had it as y equals the opposite of 10 times the square of x minus 4, that plus 5. But then GeoGebra automatically changed it when it put it up here to this other format, which I got by the algebra. You can see the vertex here at 4, 5, as claimed. We can see the x-intercepts here. So one of them was about 3.3 right here. The other one was about 4.7 right there. And again, those are only approximately true. And if we were to zoom out, we'd find the y-intercept also. But because of that negative 10, well, the negative makes this parabola upside down. Anyway, I could do some manipulations until we can find the y-intercept, which is at negative 155, so somewhere right in around here. But it's kind of hard to see it in this particular picture, but could go take a look in more detail. But what I'd rather do is maybe actually show that comparison by maybe putting in, suppose we had, what was it again? Y equals negative 10 times, in parentheses, I'm going to put the x minus 4 and square it, and that plus 5. Oh, I need to close my parentheses back here. Should have closed them there. Okay. What was oh, that's the, yeah, of course, that's the exact same thing I was looking at. What did I want to, oh, I know, I wanted to look at it without the minus 10. That was it. So I was going to use maybe just a minus, but not 10. Y equals negative of x minus 4, square that, and then plus 5. So it'd have the same vertex, but, well, yeah, it's already there. You can see it's definitely wider. So this would have the same overall shape as y equals x squared, because there's no, the a here is negative 1. So the a has to do with the orientation in terms of, is it concave up, does it open up, or is it concave down, as the two we see here because of the negative. But also it's going to tell you how wide or narrow the parabola is. The smaller this number, the wider. If I were to plug in, look at, let's say y equals, I'll just do real quick here, y equals 0.5 x squared. If you were to compare that to, let me turn off some of these others here. So if I were to compare that to just y equals x squared, what you'll find is that this is going to be wider than that. So y equals x squared, of course, would pass through 1, 1, which we're not really seeing here. We'll pass through 1, 1, which is right there, whereas this one is wider. So let me just plug in y equals x squared so you can compare those two. And I strongly encourage you to play around with this yourself. Either go online with GeoGebra or some other freeware that does this, or use a graphing calculator and compare. So let's see. Go up here. So y equals x squared is the one on the inside here, labeled as r. Can't really tell too well. So the r is right here, which goes with this curve, and the q here is actually going with the outer curve here. So the smaller the a, the wider this. And vice versa. Okay, so there's of course a lot more detail to this, but just play around with it yourself and get familiar with it, and that's it for this video.